From deep in space, it looks like a marble, with swirls of white clouds forming patterns over shades of blue, green, and brown. From a distance, it is difficult to distinguish many of the Earth's features. But closer views reveal the strikingly varied nature of the Earth's landscapes. There are tall, jagged mountains that seem to almost pierce the sky. There are gently rolling plains that stretch uninterrupted to the horizon. There are canyons whose walls form a spectacle of different shapes and forms. And deserts, where the wind creates constantly shifting patterns of sand. But such views are only snapshots of a moment in time, for the Earth's features are constantly changing. Some changes occur slowly, taking millions of years. Mountains are built up or worn down, and whole continents shift their positions. Other changes occur very quickly, sometimes in a matter of minutes or even seconds. The story of the Earth began over 5 billion years ago. Some scientists think that around this time, a vast disk of spinning gas and dust began to slowly shrink, forming at its center a huge ball of superhot gas that became the Sun, the star at the center of our solar system. Circling around the Sun, clouds of dust and other particles also came together to begin to form the planets, including the Earth. For a while, the surface of the Earth was very hot, probably looking like the lava pouring from this volcano. This lava is rock so hot that it is molten or liquid. The Earth was covered with seas of this red-hot rock, bubbling and gurgling and sending up fumes of gas. Eventually, the Earth's surface cooled and took a form more familiar to us. Today, even from space, we can see only a small part of the Earth. What lies underneath our planet's surface remains hidden from view. In a way, looking at the Earth is like looking at the shell of a hard-boiled egg. The shell is only a very thin covering. But if we cut open an egg, we can see that beneath the shell are several layers. Inside the egg is yellowish yolk, and the yolk is surrounded by white. Like an egg, the Earth consists of several layers. Even though we can't cut open the Earth, scientists have been able to determine much about what is under the Earth's surface. Like the shell of an egg, the Earth's outermost layer, called the crust, is very thin. On average, only about 10 to 20 kilometers thick. Beneath the crust is a layer of denser, heavier material called the mantle. The mantle is the largest part of the Earth. Scientists think the mantle is made up of heavy rock containing metals like magnesium and iron. The core is at the center of the Earth. It consists largely of nickel and iron. The very center of the core is the hottest part of the Earth, with temperatures reaching about 5,500 degrees Celsius. But let's return to the part of the Earth we know best, its surface or crust. This mountain in Arizona is evidence that the crust is constantly changing. The mountain is slowly being worn down through a process called weathering. Weathering is the process by which rock and other materials break up into smaller pieces. Weathering can happen in different ways. Plants can play a role. The roots of plants can grow into cracks in a rock and force the rock apart, sometimes breaking it. Ice can do the same thing. When water gets into rock and freezes, it expands with great force. Even when water doesn't freeze, it is an important cause of weathering. Water in streams and rivers carries fine particles of sand or rock that grind against larger rocks, wearing them down. Water also may contain acids that dissolve some kinds of rock. Over a short period of time, the effects of weathering may seem slight. But over thousands or millions of years, weathering can change the Earth's features in dramatic ways. For instance, the Appalachian Mountains that extend from Canada to Alabama are smooth and rounded. But millions of years ago, the Appalachians looked quite different. More like the tall, jagged peaks that are part of the Rockies in the western United States. Over time, weathering wore down the Appalachians, just as the Rockies too will eventually be worn down. But weathering is only one of the forces that change the Earth's surface. Another is erosion. Erosion occurs when loose bits of rock and soil formed by weathering move from one place to another. The wind can be a powerful force of erosion. Near the Sangre de Cristo Mountains in Colorado, the wind blows sand back and forth across a valley, moving dunes that are as high as 700 feet and constantly changing their shapes. Water is another important cause of erosion. Powerful waves can carry away sand and even large rocks and change the way a shoreline looks. Erosion also occurs when water runs downhill, as in a stream or river. The flowing water carries sediment, soil, and small rocks. To see how erosion works, put some pebbles in the middle of a pan filled with sand. Then tilt the pan slightly and pour water onto the sand. Notice how some of the sand washes down the pan, but the heavier pebbles may move only slightly. Now, try doing this experiment again, but this time raise the end of the pan to form a steeper slope. Notice how the water flows faster, and both the sand and the pebbles wash away. The same thing happens in nature. The steeper the slope, the faster the water moves, and the more sediment it can carry. As this sediment is carried downstream, it grinds and rubs against surrounding rock. Erosion and weathering together wear away the Earth's surface. The Grand Canyon was formed as the fast-flowing water of the Colorado River carved out a channel that in some places is over 2,000 meters deep. When land flattens out, water flows more slowly and sediment can settle to the bottom. By the time the Mississippi River reaches the ocean, it flows slowly enough that great quantities of soil settle to the bottom. Over thousands of years, this sediment has built up deltas. Deltas are new areas of land formed by sediment where a river empties into an ocean or lake. There are other kinds of rivers that cause erosion. Frozen rivers of ice. In very cold climates, snow may pile up over many years and centuries and gradually change to thick layers of ice called glaciers. Like the water in a river, glaciers can flow, but much more slowly. They flow too slowly for us to see them move, but they are very powerful and can drag with them great quantities of rock. As a glacier carries this broken rock, it can act like a huge bulldozer, reshaping the land as it advances. We can still see the effects of glaciers long after they have disappeared. In a New England forest near Boston, a huge boulder sits perched on top of smaller rocks. How did it get there? Glaciers offer the best explanation. This is Maureen Ramo, a geologist at Boston University.
One of the really neat things about the history of our field is it's a young field, geology, and people didn't understand the climate history of the Earth for a long time. And as recently as 100 years ago, people would debate how huge rocks like this got here. There was a whole group of scientists that thought they were left by the receding floodwaters of Noah's flood. But then there were other geologists who would look at the action of glaciers in places like the Alps or in Greenland and say, wow, glaciers can move rocks this big over long distances. And when you have that view that maybe ice could have been here moving around, you can look all around the landscape and see all the evidence for ice.
Geologists now believe that for much of the last 3 million years, glaciers buried the northeast landscape of the United States during different ice ages. As the ice advanced down from Canada, it pushed huge quantities of broken rock. And as it melted and retreated, it left behind this scraped-up debris. These sandy bluffs in Cape Cod are another example of the effects of glaciers. The sand and rocks that make up these bluffs came from as far north as Canada and were left behind as glaciers melted.
The recognition that ice ages occurred completely revolutionized how geologists interpreted the environment around them.
But there are other, even more dramatic forces at work that change the surface of the Earth. When we look at a globe, the most prominent and familiar features are the Earth's continents, the large land masses such as North and South America and Africa. It is hard to imagine there being any different than they are today. But the arrangement of the continents on the Earth's surface is only temporary, existing for this moment, but very different from what it once was and from what it will be in the future. There is strong evidence that the continents have moved and are still moving. One way of looking at the continents is to compare them to pieces of a jigsaw puzzle. When putting together a puzzle, you use a variety of different clues. One clue is shape. To assemble a puzzle, you look for pieces whose shapes fit together. The shapes of the different continents suggest that they too might at one time have fitted together, like pieces of a jigsaw puzzle. The shapes of South America and Africa, for example, seem to indicate that at one time they were joined. There is other evidence besides the continent shapes to support the theory of continental drift. Think of some other clues you use to put together a puzzle. Besides shapes, you look for colors or patterns that are the same, and that indicate that different pieces belong together. In a similar way, geologists look for clues other than shape to support the theory of continental drift. One such clue is provided by fossils. Fossils are traces of animals or plants found in rock. Some of these animals and plants died many millions of years ago. Fossil remains of the same kinds of animals have been found in locations in both South America and Africa. It is doubtful that these animals could have crossed the Atlantic Ocean that now separates these two continents, and this offers additional evidence that when these animals lived millions of years ago, the continents were joined. Scientists now think that about 250 million years ago, all the continents were grouped together in a huge supercontinent they call Pangaea. Much of what is now North America was down by the equator, and other features of the Earth that are familiar to us today were very different.
About 250 million years ago, the Atlantic didn't exist. We were one huge supercontinent. All the continents were now welded together. And shortly after that point, the Atlantic Ocean began to form. And it formed in the middle of this huge supercontinent. And slowly crack opened up in the continents that eventually got wider and wider, and eventually the water from the other oceans spilled in, and that became the Atlantic. And the Atlantic's continued to grow since that time, and it's still growing today. Every year, Europe is a little bit further away from North America.
While the evidence is strong that the continents have drifted to their present locations and continue to drift, the question remains, how do they drift? Scientists have developed a theory to explain continental drift. This theory is called the theory of plate tectonics. According to the theory of plate tectonics, the Earth's surface is located on top of large blocks of rock called plates. These plates actually float on the partly melted rock of the Earth's mantle. Heat inside the Earth creates currents in the upper part of the Earth's mantle, which is putty-like and can flow under pressure. These currents move very slowly, but they are so powerful that they can push different plates together, apart, or past each other. One place where plates are moving apart is the Mid-Atlantic Ridge, part of an extensive system of mid-ocean ridges that stretch along the bottoms of all the Earth's oceans. Running down the middle of a mid-ocean ridge is a kind of valley called a rift. The rift marks the exact boundary between plates. As the plates move apart, hot liquid rock from deep within the Earth pushes up through the rift and onto the seafloor, where it cools to form new crust. A place where two plates are moving apart like this is known as a spreading boundary. But what happens when plates collide? To see what happens, take two towels. Imagine that each towel is a separate plate. Now slowly push the towels together, and note how they bunch up when they collide. The same thing happens when the Earth's plates collide. Mountains form when the land buckles upward. It can take millions of years for such mountains to form. But at the boundaries between different plates, changes in the Earth's crust also can occur very quickly. In fact, we can witness some of these changes as they happen. Volcanoes erupt when magma, hot liquid rock from inside the Earth, forces itself through the Earth's crust. Many volcanoes occur near colliding plates. As the crust of one plate collides with another, it is forced underneath into the Earth's mantle, where it melts, forming magma. The magma may then move upward through cracks and openings in the crust. The heat and gases trapped in the magma can build up pressure until finally it explodes out onto the surface. Earthquakes provide another example of changes that occur suddenly on the Earth's surface. In 1994, much of Northern California was rocked by an earthquake that caused extensive damage. Buildings and highways collapsed. The earthquake destroyed whole neighborhoods and forced people to abandon their homes. What are the causes of such destructive quakes? Once again, plate tectonics provides an important clue. The San Andreas Fault in California, the site of frequent earthquakes, marks a boundary that you can actually see where plates slide past each other. As these two plates move past each other, they exert enormous pressure on the surrounding rock. What can happen can be compared to what happens when you slowly bend a stick. The more you bend it, the greater the stress, until suddenly it breaks. In a similar way, earthquakes occur when rock bends as plates move under a great deal of pressure. Like a stick, the rock can suddenly break, releasing a great amount of energy that causes the ground to shake. Along the San Andreas Fault, scientists are trying to better understand this process by actually drilling deep into the boundary between two plates.
The drilling project is an attempt to get into the San Andreas Fault in a place where small earthquakes occur and where creep is occurring along the fault. We want to measure the basic forces that drive the fault, understand the fluids that help in its motion, understand the minerals and their strengths that occur within the fault zone, basically to try to understand the clockwork of the San Andreas Fault.
By better understanding what happens along fault zones, scientists hope to be able to more accurately predict earthquakes and reduce the amount of destruction they cause. But today, humans themselves may be changing the Earth in ways that are destructive. One example is climate. Part of the Earth consists of a thin layer of gases that make up the atmosphere that surrounds the Earth. Scientists think that the burning of fossil fuels such as gasoline may be causing changes in the atmosphere that are leading to a gradual warming of the Earth's climate. Among other consequences, such global warming could lead to a rise in sea levels. Low-lying areas such as Florida would be in danger of flooding. While changes in climate have always been a part of the Earth's history, what is happening now may be different.
What's different about what mankind is doing is that the rate and the speed at which we are changing the atmospheric composition is almost unprecedented, is unprecedented.
In this program, we've seen how the Earth is made up of different layers, including the core, the mantle, and the crust or outermost skin. We've looked at some of the ways the Earth's crust can change. In the process of weathering, rock is broken up into smaller and smaller pieces, and in erosion, weathered material is transported from one place to another. We saw how glaciers covered much of the northeastern United States and had an impact that can still be seen on much of the landscape. We looked at the theory of continental drift. This theory suggests that the positions of the continents that we see on a globe are very different from what they were millions of years ago. The theory of plate tectonics provides an explanation for how the continents drift. According to this theory, the Earth's crust lies on top of different plates, and currents within the Earth move these plates in different directions. We've seen how the boundaries between plates are often sites of great activity. At the bottom of the oceans, lava forms new crust at mid-ocean ridges where plates are moving apart. And where plates collide, the crust may buckle upward to form mountains. We've seen how volcanoes erupt when magma that normally lies below the Earth's surface forces its way through the crust in an often spectacular display of natural fireworks. And we've seen how earthquakes can release enormous amounts of destructive energy that literally shakes the Earth. Finally, we've seen that humans too may be changing the Earth. The burning of fossil fuels may be causing atmospheric changes that are leading to a warming of the Earth's climate. All these things emphasize the most important lesson of all, that the Earth is ever changing, and the planet we know today is very different from what it was in the past and from what it will be in the future.